Hi, I'm Zach Saratella, and I'm here with Hans Luchsinger and Zach Schroeder to talk to you about our senior design project, the Hive Cartography system. Every day, firemen, EMTs, and police officers risk their lives by going into high-risk areas where they don't know the layout or structural stability of their surroundings. If they had more information about their floor plan as they were searching, they would have to spend less time inside, and thus their risk of loss of life or injury would be greatly reduced. With our design chosen, we came up with 15 engineering requirements to tailor our general requirements to the project specifically. In order to keep it easy to maintain, the system will be rechargeable by a wall charger in under 3 hours per robot. In order to make the robots easy to use, we want the robot to backtrack to the starting position if it loses connection from the hub. The time to deploy 2 robots from unpacking to mapping should take no longer than 5 minutes. The hub should be launchable from a single executable file, and the map will be saved and reopened from a single file. For our accuracy requirement, we wanted our generated map to be accurate within half a meter. Portability was ensured by requiring each robot to be no larger than half a cubic meter and that each robot weigh no more than 10 kilograms. For our battery life requirement, each robot should be able to operate for half an hour before being recharged, while the hub should be able to operate for 45 minutes before being recharged. To keep it low cost, each robot should cost no more than $500, and the hub peripherals should cost no more than $100. To ensure quickness, a single robot should be able to map a 5 by 5 meter room in less than 5 minutes, and the system should display a 2D map that is updated within half a second of a new data point being received. To make sure that the system is robust, each robot should be able to survive a drop of a quarter meter without interfering with normal operation. For our case, we wanted to design something that was robust, simple, and stylish. We chose tank tracks over wheels because tank tracks maximize friction and minimize slipping. The case itself was made of brass because it is non-ferrous, to keep from interfering with the magnetometer, and because the gold color was aesthetically pleasing. The inside of the case has an upper and lower compartment. The lower compartment houses the battery, motors, wheel encoders, proximity sensor, and on-off switch. It is separated from the top compartment by a 1/16 of an inch thick acrylic sheet. The top compartment houses most of the circuitry. This includes the 3 ultrasonic sensors, the voltage regulating and motor control board, the FPGA, the magnetometer, and the Raspberry Pi. Our power block consists of a 14.4 volt, 3.3 amp hour nickel metal hydride battery pack and a voltage regulating circuit based around a Texas Instrument dual channel synchronous buck converter. The buck converter takes in the 14.4 volt output of the battery and steps it down to output 6.5 volts on the first channel and 5 volts on the second. The 6.5 volt output is sent to the motor control circuit, while the 5 volt output goes to all of the sensors, the FPGA, and the Raspberry Pi.
Several sensors were chosen in order for the robot to be aware of its environment and take measurements for the mapping process. The core data that we wanted was where the robot was located and how far it was from surrounding objects. The location was able to be determined by using a combination of DF Robot 3PA wheel encoders and a Polulo LSM 303 DLM compass and accelerometer module. The ranging of the robot's surroundings was done using Devon-Tech SRFO2 ultrasonic range sensors positioned at the front, left, and right of the robot. Finally, an IT'd infrared proximity sensor was added to the front of the robot in order to sense drop-offs and prevent the robot from falling and damaging itself. The low-level functionality is controlled by a Lattice Mach-X02 FPGA. Its primary responsibility was to control all of the sensors and communicate with the Raspberry Pi. Communication with the Raspberry Pi was implemented using the SPI serial protocol and was set up so that the Pi could request sensor data or send controls to be outputted to the motors. Interaction with the ultrasonic sensors, the compass, and the accelerometer was implemented using an I2C serial bus, as specified by the sensor manufacturers.
The software for a robot can be broken into 3 main parts: the onboard mapping and navigation, the communication server, and the hub's graphical user interface. The onboard mapping and navigation software was written in C and is installed locally on the Raspberry Pi. It is in charge of collecting sensor readings from the FPGA and interpreting them into localization and map data. In order to keep track of where the robot is, a dead reckoning localization algorithm is used. The robot then uses this localization information in combination with the collected data to recreate the area around it. The robot then makes a decision about what the best path for it to follow is in order to maximize the mapping of unexplored areas. Paths which are not selected are then marked for later exploration and sent out to any other robots in the system through the communications server. This allows the robots in the system to work in cooperation, picking up routes from others as they complete their own in order to map as quickly as possible. The communications server, written in C, is installed on the laptop and gets launched at the same time as the hub's graphical user interface. The communication server sets up an Ethernet port on the laptop that the drones and user interface can connect to and is used to pass data between them. Strings of data are received from the robot and are copied by the server and sent out to all other robots and hubs that are connected to the system. This ensures that data is passed to all members of the system, fully distributing all of the information in case any one element fails. The hub's graphical user interface was written in Java and is installed locally on the laptop. The user interface receives localization and map data from the robot, interprets it into a human-readable map, and combines it with previous map information, as well as the map data from any other robots in the system, to generate an updated map of the area. It then renders this map as a bitmap image and displays it to the screen, giving the user options to zoom and pan the image, or save it for later viewing. All distance information is preserved in the rendered image, and the user can use the mouse to drag and measure any distance that they wish.
Hi, my name is Zach Schroeder, and today I'm going to be walking you through a demo of the Hive Cartography system. What we'll be showing you is a startup procedure and then the real-time mapping of the room that I'm in right now.
First, the laptop and robot are powered up. Waiting for the two devices to establish a connection is one of the longer parts of the startup process. So, to speed up the start of mapping, we've left the laptop acting as the hub on. While the Raspberry Pi initializes on the drone, the map interface and the hub program are launched on the laptop. This is done using a single executable file in order to make the startup process incredibly simple for the user. This program is written in Java and has the capability to be ported to other devices, like a tablet or a smartphone. When the blue LED on the rear of the robot begins to flash, the operator knows that the robot is finished initializing and a connection can be established. After the operator notices that the robot is prepared, an SSH connection is made to the drone and a script is prepared to be launched before the drone is placed in a starting position that corresponds to the orientation of the map. Each robot that connects to the system receives a different prioritization scheme for path decisions. This particular one is prioritizing forward unexplored paths, then right, then left. Once the robot is set down, all that's left is to hit enter and let the mapping begin. The mapping process begins with a 360-degree turn, measured using the drone's onboard magnetometer and timed using the Raspberry Pi. The timed spin adds redundancy in the system so that the absolute magnetometer rotation can be confirmed using the relative change in timing. Once complete, the robot starts by driving forward. As the robot drives forward, you'll notice it making small course corrections. These are done by monitoring the heading and making adjustments to the motor as the path gets off. There are occasional glitches in the system due to inconsistent magnetics in certain areas. This problem could be easily remedied by implementing better redundancy checking and higher precision wheel encoders. The mapping process is unfortunately interrupted at the end when one of the wheel struts catches a crack between tiles. Remember that this is an early proof of concept prototype and these issues will be worked out later. Here you can see what the map looked like as it was generated on the hub laptop during the mapping process. The curved wall and the approaching hallway intersection are clearly shown with only minor glitches, proving that the robot was functioning until its mishap.
Hi, I'm Hans Luchsinger. Now that you've seen a bit of how and why we've created a device like this, as well as our initial prototype design, I hope that you can see the real-world applications of a system like ours. Further development of hub and satellite technologies could speed up search and rescue operations, decreasing the risk to people entering the search area. This is one of only many possible implementations of this technology, and it's only with your funding and support that we, and companies like ours, can protect our society's heroes. On behalf of Hive Cartography, thank you for your time.